Okay, I've got a screencast here. We're just going to kind of get going on a worksheet by the end of the screencast. I want to review a couple things about projectile motion with you to help you with the worksheet. And let's define two-dimensional or projectile motion for you in a little more detail. Projectile motion is actually the motion of an object. It's in free fall, but it's with a component of horizontal velocity. So it's not just dropped, it's got to have some component of horizontal velocity to be a projectile. So when you hear me use the word projectile motion, think of anything that's up in the air. Pretty much when we talk about projectiles, it's airborne, it's in free fall, only gravity acting on it, but it's moving sideways at the same time, like a baseball, football, soccer ball kicked, a missile that's launched, a bullet that's shot, all different kinds of things. I've got a video here I'm going to show you. This is exactly what was on my screen the other day. This is the horizontally launched projectile and the one that's dropped straight down, and we compared the times. Remember that? So I'm going to go ahead and play this from the beginning. They land at the same time, and that's what we saw on our video yesterday on our screen on our Zoom meeting. So let's look at this in a little more detail. So I'm going to go frame by frame in this one in this video, and notice two things as this advances. One is that the x component of the ball on the right, the one that's got the horizontal velocity, it doesn't change. The horizontal velocity stays, I should say the x component of velocity of the right ball doesn't change. And the y components, I misspelled, of velocity of each ball are exactly the same at the same time. So as they fall, the y component of velocity is exactly the same. So let's play this and you'll see what I'm talking about. So as it starts, notice that the x component of velocity here as it's going down doesn't change. It's 6 the whole time down, and the y component of velocity is always the same. I'm kind of chasing it here, but you can see what I'm talking about. It's always the same between the two. So that explains why they land at the same time. So let's let's explain why they land at the same time. Let's look at it in a little more detail. The force diagrams of the two balls are exactly the same. Here's the force diagram for ball 1. Here's the force diagram for ball 2. The only force acting on them is the mass times g of the two objects. So they're both in free fall. There's no air resistance or anything like that. Both balls start with a 0 initial velocity in the y direction. So even though the one ball has a horizontal velocity, ball 2 is moving with an initial horizontal velocity, that doesn't affect its y velocity. Its y component of velocity is still 0. And both have the same acceleration. They're in free fall, so they fall at 9.81 if it was no air resistance at all. And they fall the same distance. So the delta y of object 1 and delta y of object 2 are exactly the same. And so the result is the times are the same. You start something with the same velocity and give it the same acceleration and have it cover the same distance. It's going to do that in the same time. So that makes sense. We're going to look at the worksheet now. So this is worksheet 1, or actually I think it's called worksheet 2 on Schoology. It's the first worksheet that we have in the 2D motion unit. So I'm going to actually work through this with you on the first problem, and then I'm going to have you do page 2 yourself. This problem says, given the following situation of a marble in motion on a rail with negligible friction, that means no friction, sketch a motion map showing the marble after it leaves the rail. So here's the marble here. So after it leaves the rail, so we're going to start when it's right here, using the grid to help you carefully locate the marble's positions, show horizontal and vertical velocity vectors on each dot. So if this is my vertical velocity, I'm going to show the same vertical velocity right here. Since it's just left the rail where I drew it, it doesn't have any y component velocity yet. It just left the rail. So I'm going to go, let's see, I'll go over horizontally 2 grid marks, and I'll come down 1 grid mark in the y direction, and it's x component of velocity. I should show that here too. Hasn't changed a bit, but now it's gained a little bit of y velocity. So I'm going to show a little y velocity there. Vy. Now in the next time interval, let's say 1 second, it's going to travel the same distance horizontally because it's not accelerating or slowing down in any, going faster or slowing down in either direction horizontally. So it's going to cover 2 spaces horizontally, but I'm going to have it cover a little more distance vertically because of the fact that it is accelerating in the y direction. So my y velocity has picked up. I have a longer vector here on the y direction. The next one's actually going to be off the grid because I have to go 2 sideways again in the x direction, but I want to go, if I just went 2 in the y direction between the last time interval, 2 grid spaces in the y direction last time, I'm going to go 3 grid spaces, which kind of takes me off of the grid. I'm going to be somewhere down here. Same length of Vx vector, but my Vy is going to be even longer. So that's what that would look like if I drew a motion map of this thing falling off the edge of the table. And it's actually, it's going to hit the ground before that moment. So it's kind of unrealistic what I just did. But you understand that I'm going the same distance each time interval in the x direction, but I'm increasing in vertical displacement each time interval, if that makes sense. And my y vector gets longer. Sketch and label the I'm in B now. Sketch and label the force diagrams for the marble when it's on the rail and off the rail. So on rail, it's got the earth pulling down, and of course it's got the table up, and it's a balanced force diagram, and it's rolling at constant speed because there's no friction. As soon as it leaves the rail, there's no more normal force, right? Now it's in free fall, so its force diagram is just mg. So that's why you see the motion, the Vx doesn't change, but the Vy goes from 0 to something bigger than 0, right? That's what you're seeing over here. Starts at 0 and it increases in length. So now we actually have to do a calculation in part C. So I'm going to go to the next page. Part C says, once the ball leaves the table, how long will it take to hit the floor? So we have to look at the y direction to answer this question. The x direction isn't going to help us because I have constant velocity in the x direction. So I have to look at all of the information in the y direction. So just like we did before, I have to list all the things that I know. I know my delta y. I got to go back and look at that real quick. Delta y is 1.5 meters. The initial velocity in the y direction is 0. My acceleration in the y direction is g, negative 10 meters per second squared, and that makes me think that my delta y, I actually have to go back and edit that. That's a negative 1.5 because I'm dropping. It's falling to a lower height, so I have to have a negative displacement in the y direction. And they want me to find time in the air. It's just like as if I dropped it. Notice I'm completely ignoring its x velocity. This is the same calculation we would have done if we were dropping something from a height of 1.5. And if you go through your list of kinematic equations, it's invisible woman that makes the most sense to use here. That looks like that. And I have an initial velocity of 0 in the y direction. So I'm going to say delta y. If I solve for time, I rearrange this. I multiply both sides by 2. I divide by the acceleration, which is g, and I take the square root. I did a lot in one step there, but that's basically rearranging that equation to solve for time. And so 2 times negative 1.5 divided by 10 and take the square root of that. It's basically the square root of 0.3. I'll let you find the answer to that. How far will the ball travel horizontally? Actually, I'll have to calculate that because we want to figure that out. No, I can just use that answer. Never mind. I'm not going to calculate it. I'm going to jump down to D and say, in the time you've calculated in part C, that's this time right here, that's the time the ball's in the air, how far will the ball travel horizontally before hitting the floor? Well, remember, its velocity in the x direction, it started out at 10 meters per second, and it hasn't changed. It's moving at 10 meters per second the whole time. So the only equation I'll ever need in the x direction is the constant velocity equation. And if I want to know what the displacement is, I want to solve for delta x, it's just Vx times time. So once I know my time from up above, it's just 10 meters per second times the square root of 3, which was whatever that was from up here, and that's going to give me the displacement in the x direction. The only variable the two directions share in common is time. And the reason is time is a scalar. Direction doesn't matter for time. So it's in the air for the same amount of time in the x direction as it is in the y direction. So once I use the y direction to find the time in part C, I can use that time in part D to answer some questions about what happens in the x direction, because it's the same. I'm going to let you do this. Now that we've solved part D, you can say if you double the height to 3, so instead of delta y being 1.5 meters, now it's twice as high, 3 meters. What does that have on the range of the marble? The range is the horizontal displacement. So whenever you see that word range, you're talking about the horizontal displacement. Okay, so I want you to finish page 2 for Monday. Page 2 is just these two problems here. Similar things where the marble is going to leave the table horizontally. Anytime it leaves the table horizontally, your V0 in the y direction is going to be 0. So you just have to do, it's a slightly different situation here where you're going to have to calculate the horizontal velocity based on the information given in number 2. And then they give you a little different scenario in problem 3 that apply, problem 2 information modified slightly for 3. Okay, good luck. I hope you guys have a good weekend and this makes sense to you. We'll have a Zoom on Monday. I'll answer questions. Take care.